Electron Configuration Part 2. After this video, you will be able to write the electron configuration of an atom up to barium, which has an atomic number of 56. Now, I'm already assuming that you can write electron configurations up to argon, which has an atomic number of 18. And I'm also assuming that you already understand the Aufbau Principle, the Pauli Exclusion Principle, and Hund's rule. If not, then you need to go back and look at Part 1. In order to draw electron configurations beyond argon, we need to know a little bit about d orbitals. Now, an atom has 5 d suborbitals, each which can hold 2 electrons. So that means that in total, a d orbital will be able to hold 10 electrons. Let's look at scandium, for example. It has the electron configuration of argon, so we can write our symbol for argon in brackets, and then we start with 4s to 3d1. 4s to 3d1. Now this is kind of weird because the 3d orbital is at a lower energy than the 4s orbital, but the 4s fills up first, and then the 3d fills up. Now there is a reason for this, but that's beyond the scope of this video. But just remember that the 4s, the s orbital, will fill up before the d orbital. Now after you finish filling up the electrons in the 3d orbital, which comes after the 4s orbital, then you go on to fill in the 4p orbital as normal. And we will see that with our example, bromine. There goes our electron configuration for argon up to 3p6. And so we write the symbol for argon in brackets as we begin our noble gas configuration. And then we start to fill in 4s2, and then we go down to 3d10, 5, 6, 7, 8, 9, 10, 3d10, there we go, and then we go up to 4p5, 4p5, and that is our full electron configuration for bromine. Now there are a couple of exceptions when filling out the 3d orbital, which makes it kind of tricky. Chromium and copper. These don't follow the normal rules. Let's take a look at chromium. We start out with the argon configuration, put that in brackets, and then we will go 4s2, 3d4. And that's how we would normally do it, right? Wrong. This is actually not what it looks like. Let's try it again, right this time. There goes our argon configuration. And we go 4s1, 3d5. And so what it appears to happen is that we have a half-filled s orbital and a half-filled d orbital. Now, the reason why for this is beyond the scope of this video, but you have to just remember this exception. Now, for our next exception, copper. By now, we're familiar with our good old argon electron configuration, and for copper, we would go, you would think, 4s2, 3d9, 5, 6, 7, 8, 9. But, as you probably have guessed, that is not correct. So, what is the way that copper's electron configuration is actually written out? Well, there's our argon configuration. There we go, everything up to 3p6. And then it is 4s1, 3d 10. So the 3d orbital is completely full for copper. But as you can see, this anomaly, the 4s orbital, only has 1 electron. Now, the reason for these exceptions, they're beyond the scope of this video. I don't want it to be too long, but you can ask me, and I'll be happy to explain to you why. And there you have it. So after watching this video, you should have learned how to write the electron configuration of any atom up to barium. That is because I didn't really go over the f orbitals. It follows the same pattern, but I'll say that for another video, maybe, if it's necessary. You also know the Aufbau Principle, the Pauli Exclusion Principle, and Hund's rule. And if not, feel free to go back into the video to clarify those concepts.